Right, so insertion sort. There's a very clear way to show that you're doing insertion sort, and it's really important that you talk about the premise. Insertion sort assumes that an item with one item in it, a list with one item in it, is sorted because it's only got one thing. So we always start like this. So we do square brackets to show the sorted list, and then we write everything else down in the unsorted list. And then what we're going to show is how we position each item one at a time. So our first, and some of you did this correctly, you went key equals 0, so the one we're trying to insert. You start off before you do anything and you make your array capable of holding 2 items, because there will be 2 things in the sorted list. And all we're going to do is we're going to look back and we're going to go, right, 0 is less than 2, so 2 needs to move across. So 2 moves across. We've then found the insertion point. So you can, when you're doing this, and I'll do it on this next iteration, you can actually write the unordered list out at the start before you do the thing. So let's do that this time. So the next time we're going to try and insert a 1. So let's leave space for 3 items. So I'm using where I've drawn them to do that. And I'm just going to write the unordered list. So what we have remaining is 7, 4, 3, 5 and 6. But we're going for 1 at the minute. Right. So 2's bigger, so 2's going to shift. 0 is not bigger than 1. So we've found our insertion point. Okay. Let's go again. So the next value is going to be 7. And the way they mark this, they didn't give you a mark per row. It was grouped, wasn't it? So they're saying this is slightly easier to demonstrate. Right. So there will be 4 items when we've finished. So let's make the sorted list capable of holding 4 and write down the unordered ones. Notice I write the key value down first. Right. So this time we say straight away, 2's less than 7, so we've actually found the insertion point. So we didn't have to do any work at all really there. So that's one of the things that makes insertion sort quick, if the numbers are partially sorted. Right, we're going to go for the next iteration, which is going to be placing the 4. So let's make space for 5 items. So I'm just trying to keep this neat. Right, so when we start, and I'm going to write those ones out. So we've got 3, 5, 6. Right, 7 is bigger than 4, so 7 moves across. 2 isn't bigger than 4, so we've got the insertion point. So I'm going to write everything down and insert me 4. Going again. The next one to insert is 3. So I need space for everything including that 3, which just leaves me with 2 unsorted items. Although we as humans can see they're sorted. Right, so 3. 7 is bigger, so that needs to move across. 4 is bigger, so that moves across. 2 isn't, so we've found the insertion point. So 0, 1, 2, 3. Second to last. Make space for all including the 5. And then 6 is on its lonesome. Right. 7 is bigger than 5, so that moves across. 4 isn't, so we've found the insertion point. Stick it in. Final one to do is our 6. So that's going to be space for all the data items this time. Right, okay, so 7's bigger, so that moves across. 5 isn't. So we've found the insertion point pretty quick. That's it. Quite straightforward if you do it like that. Don't ever let anyone think you're doing bubble sort or do some sort of mixture of bubble sort and whatever sort method you're making up at the time. There was a lot of that going on. Right, okay, so moving on. Quicksort. And he said describe. So the mark scheme is quite weird. If you just showed quicksort working, you only could get 4 marks. So you had to say something about it. Okay, so you need to say something to do with the left and right pointers. So place left and right pointers at extent of list. Okay, pick a pivot value, associate with left pointer, because it doesn't really matter. And the algorithm's purpose is just to make sure that everything's smaller. So when the algorithm finishes its first pass, when that's complete, everything to the left of the pivot will be smaller because we're going ascending. That'll be smaller. And everything to the right should be bigger. And that will give us two lists to quicksort, which we can do in parallel, can't we? So, obviously this is a piddly example, but in reality, so this leads to... So that's really all you ever need to explain about quicksort. You can say it's divide and conquer and it's recursive, but you can implement it non-recursive. So this leads to two unsorted lists that can be independently quicksorted. What else can you say about quicksort? What type of sort is it? Is it an in-place sort, or is it a extra space sort? Do we have to create new lists in order to do the sorting? It's an in-place sort. We don't have to create any extra space. Remember, that's the only Achilles heel of merge sort, is that you need extra space. Right, and then to demonstrate it, we need to show the left and right pointers working. So let's just write these numbers down. And they actually were quite kind with this, I think. There wasn't much movement to go, was there? Right, so we're going to set up left and right pointers and a pivot value, and we're just going to show them moving in. So we're going to compare left and right values and then swap if wrong order. And we're going to stop when left and right pointers are the same. And that's the pass complete. Right, okay, so I've got 2 and 6, they look okay. So the one not associated with the pivot comes in. 2 and 5 are okay. Move the pointer in, not associated. 3 and 2 are okay. 4 and 2 are okay, so we're moving on here. 7 and 2 are okay. Then we get to our first move. So we need to swap the 2 and the 1. So we move the 1, and remember, just do it like that so you're not rubbing it out, and then we move the pivot, because obviously the pivot value was 2. So the pivot is had to move. So cross that out, mark it, and then we move the pointer in that's not associated. So the left pointer then goes in. 0 and 2, they're in the right order, so the left pointer moves in. That is our stop. The pivot is in the correct place. But we've now got two potentially unsorted lists that we can quicksort independently. So we can quicksort 0 and 1, or the 1 and 0, and then the 7, 4, 3, 5, 6. And if we've got multiple CPUs or threads, we can do those independent of each other, because they're not in contention for memory, which is one of our key things for doing things in parallel. If you've got no memory contention, it makes it simple. Anyone got any questions about that?
Yeah, so you said just to do one pass.
Yeah. I mean, it didn't say it, did it?
Yeah, that's what I was going to say. Is that just something that, that
In general, with the quicksort, because it takes forever, doesn't it?
yeah.
They're not going to get to do more than one pass. If they wanted to do 2 passes, then they would have to say. But there's nothing to stop you saying when you finish that, saying, right, this needs quick sorting and this needs quick, just to cover yourself. And you've demonstrated it.
Half done, because I didn't want it to look like it was half
No, I know, that's the problem. Yeah, and you did do it all. But it's time, innit?
Yeah.
What was that? 6 marks. So you've got like 7 minutes or so to do it. Not easy. It's not the nicest one to demonstrate. Right. Okay. I'll just stop that there and I'll.